Kyunghyun is from New York University, and he will give the second lecture of the day on NLP. And welcome, and thank you for joining us.
Well, thanks for the generous introduction. Yes, it's Kyunghyun, and then the Bjorka, you had the perfect pronunciation there. And then nice to meet you all. Hope you're all enjoying the summer school. Summer school, yes, summer school so far is virtual, but virtual summer school so far. So yeah, just to introduce myself, I am an associate professor at New York University. And then I'm going to mainly talk about the work that I did while I was at Facebook AI Research. I was there until recently, but I kind of quit. So unfortunately, I can't get any of you as an intern at Facebook AI Research anymore. But I'll be happy to answer any questions if you have anything about the either New York University or the Facebook AI Research on Rocket Chat. I'll be there online mostly this week. So, so I heard that you learned about some basics of the natural language processing from Tomasz earlier today. And then I thought today, for my lecture, I'm going to focus on the evaluation part because it turned out that evaluation is very, very difficult. But before going into the evaluation, let's talk about why evaluation matters now more than before. So, when we think about the natural language, on one side, there is generation. And then, of course, generation assumes that we do have some kind of understanding of language or the text. Because without understanding, can you actually generate some, let's say, well-formed and meaningful text? That's always a big question. So let's look at two news articles on the slide. On the left-hand side, there's an article from CNN. On the right-hand side, there's an article from TechCrunch. Both of these articles talk about the startup, two different startups that focus on pets, right? Essentially, trying to build an Uber for walking dogs. Okay, that's kind of weird startup, but it turned out that there are a few of those startups there. Now, I'm going to give you about 20 seconds, we don't really have tons of time, to quickly look at the title and perhaps the first couple of sentences. Now, does any of these two articles look weird to you? Is it possible that one of them or both of them was written by a machine rather than a human journalist? It turned out that in fact, one of these was indeed generated automatically, given a title only. So I'll just give you the answer. Only if we had like tons of time, we could have actually read it like very carefully. On the left-hand side is the actual CNN article written by the journalist Sarah Ashley O'Brien at CNN Business. On the right-hand side is one of the examples from the paper written by Zellers et al. 2019. And then except for the title and which magazine it was supposed to be written in, the whole article was generated automatically. And then if you had read it, and then if you're not one of those VCs who have invested in the dog walking companies, then you would never be able to tell whether the article on the right-hand side was generated automatically. But unfortunately, the thing is, generation is never going to be perfect. And the reason is not because the machines are not good at writing text or they're not good at generating any kind of structured output. We know how to build these machine learning models to generate these amazing text very, very well. I heard that you're going to have a lecture by Lukasz later on about how to build a transformer to generate amazing text. So the issue is that the text is by definition fake. So if you think about images, let's say you take a picture of the word. What happens is that you're going to take a picture of the word as it is. Of course, there will be some distortion due to the choice of your lens. And if you use Snapchat or something like that, you're going to apply some kind of filters. But generally, if you took a picture of a cat, then the cat exists there in the scene. So no one is going to say that oh, that's a dog when they look at a cat. But when it comes to text is, natural language is by definition fake because we ourselves made it up from scratch. There's no such thing as natural language in nature. So it's kind of weird to call it a natural language to start with, in a sense that whenever there is a something happening, and then let's say a bunch of people look at the event and then trying to describe it, every single one of them is going to have their own version of the description of the event. So what it means is that the generation is kind of by construction imperfect. And then what we see is that the machines do make these imperfect generation, do generate more imperfect text. But then the thing is, as the capability of generation gets better and better, it becomes more and more difficult for us to tell whether the generated text is imperfect or not. So on the slide, on the left-hand side, there is an article from The Guardian about the football match or the rugby match. And then there is a machine-generated summary on the right-hand side. Now, this summary is definitely imperfect. It's far from being perfect because it actually does make up a lot of, like the facts that is not facts. But then, unless you actually looked at the original article yourself and then compare this summary against the article, it's impossible for you to tell the quality of this summary based on the summary alone. You look at this summary, you notice that this summary makes sense, unless you actually know what happened. So that's why we actually need to think about the evaluation even more carefully now, because all this amazing generation does imply that it's increasingly more difficult for us to evaluate how well the generated text is. So today, I'm going to focus on the so-called open-ended text generation, where there's no single right answer. Think about writing a summary. If I took, let's say, an article from New York Times, and then I want to summarize it for the K-12 students, let's say high school students, I'm going to generate one type of summary that's going to be very different from a summary that I would generate, for instance, for the finance professionals. So what it means is that there is no single right answer. There are many different right answers with the varying levels of details and breadth. So that's what these two properties characterize the open-ended text generation quite well. For instance, there is a story generation, poem generation, all those chatbots that you can imagine and you may have actually already interacted with, and then lyric writing and summarization all belong to the category of the open-ended text generation. And we're going to focus on the summarization because that one is actually useful, unlike, let's say, lyric writing. I mean, it could be, but in the future, not much. So when we think about the summarization, there is one particular evaluation metric that everyone tends to use, and then that is called ROUGE. And then it was proposed in 2004 by Lin. And there are many different types of, or the variants of the ROUGE. And then the two major ones that are being used is the ROUGE-N, that is the n-gram recall between a candidate summary and a set of reference summaries. That is, we're going to look at a bunch of human written summaries. And then now we look at all those n-grams that are included in these reference summaries. And then we're trying to see how many of those n-grams have been recalled in these machine-generated summaries. So it's a recall measure. And then the other type that is widely used is so-called ROUGE-L. Now this one, instead of looking at the n-grams, this metric looks at the longest common subsequence between candidate and reference summaries. Now, because we're now looking at the longest common subsequence, it's effectively a dynamic n-gram that we're going to look at. So this n can be very, very long. So we're considering all possible n-gram matches, and then among them, we're going to take the n-gram match with the largest set. But anyway, so these two are the most widely used ones. But on top of that, everyone is going to report BLUE score. Everyone is going to record perplexity using an off-the-shelf language model, blah, 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 because they need to write a paper and they show it to demonstrate that they got the state-of-the-art system. Out of one of many of those, according to one of many of those metrics, to please reviewers. But these two ROUGE scores turned out to be widely used, weirdly so. So then you start talking to the summarization researchers who have been working on this for decades, and then we're going to ask them what they think of ROUGE in order as an evaluation metric for a summarization system. And then the funny thing is that almost everyone you talk to is going to tell you that that's a horrible evaluation metric to use in order to tell the quality of summary because of the many different reasons. And then two out of many of those main deficiencies include, first one is that it actually compares against a reference summary. And then if you recall the definition of the open-ended text generation, we now know that that's a horrible way to go because there are many different right answers. And then the reference summaries, however many reference summaries you're going to collect, is that they are not going to be enough to cover all possible ways in which a good summaries can be generated. And the second thing is that these n-gram based approaches or the word matching based approaches don't tend to capture the importance or the important aspects of the text. That is, these metrics weigh all portions of text equally. And then it really doesn't really care whether the factual consistency or inconsistency exists or not, because they are just insensitive. Some of those functional words are as important as many of those important nouns or the verbs that you see there. So these metrics cannot really distinguish between the important salient sub portion or the portion of the text versus the, all those, let's say, boilerplate text in these summaries. On the other hand, if you read the actual papers where the new summarization systems are proposed almost every month or so, what you see is that every single paper is going to talk about how awesome their systems are based on how high their ROUGE score, how high their system achieved in terms of ROUGE scores. CAO 2017, ends their paper by saying that, we now built the state-of-the-art extractive summarization system by at least 2 ROUGE points. And then Paulus et al. 2017 also boasts that their model obtains 41.16 ROUGE 1 score, which is an improvement over previous state-of-the-art models. And then 2018, Kaczynski et al. Also said that our model is state-of-the-art as determined by ROUGE score. Of course, Kaczynski et al. kind of, let's say, came around in 2019 saying that, ROUGE score is not that great. But until 2018, everyone was boasting that their systems were amazing because the ROUGE scores they get is just state-of-the-art. But then, that's so weird. It's really weird because, you talk to the actual summarization researchers, and then they all tell you that ROUGE score is not the score that we want to use. Or perhaps they would even say that we should actively avoid using those scores, right? So let's try to make sense of these two claims, because it's quite important when you try to do research on machine learning, because there are two things you want to do. One is that you want to build a system that actually solves the problem that you want to solve in downstream. And then in that particular case, this kind of n-gram-based metric for summarization or evaluating the quality of the summarization system are not ideal, because these metrics do not actually tell you whether the summarization system you have built actually is good or not. However, on the other hand, because we are interested in building a machine learning algorithms that allows us to use the data or the existing data that has been collected in order to build a system with an arbitrary objective function. So in that case, we can, of course, try to test our machine learning system or the machine learning algorithms with whatever the metric you want. So ROUGE is going to be fine, except that what you're going to show is that you have actually come up with a machine learning algorithm that is able to improve this non-decomposable n-gram-based metric rather than building an actual summarization system. So it is kind of confusing, but it's a weird, let's say, dichotomy that we need to work with, in the sense that we need to think about, okay, so what are we actually showing? Are we actually trying to build a downstream system that actually works for the purpose or the problem that you want to solve? Or are we trying to come up with a machine learning algorithm that works for any kind of objective function that you want it to work with? And then one of them could be the n-gram metric that has absolutely nothing to do with the quality of the summarization system, or in general, natural language generation system. But today, I'm going to focus on the first part. So we want to use these machine learning algorithms to actually build a summarization system. And then to do so, we want to come up with the evaluation metric that actually measures the quality of the summarization systems. So let's make some historical lessons. That's always a fun thing to do. And then one thing that we all learn as soon as we start looking at the summarization or the automatic summarization is that the intrinsic evaluation is really hard. Now, what do I mean by intrinsic evaluation? It means that we want to check the quality of the summary on its own. That is, I don't really care who's going to read this summary. I don't really care how this summary is going to be used. But all I care about is how good this summary is on its own. But then, of course, in order to answer this question, we need to ask the first question, or the question that is at the beginning of everything about the evaluation is that what is the quality of a summary to start with? What is this quality? It's almost a philosophical question. And then it's also very much dependent upon the context in which this summary appears or is generated. So because it's kind of difficult to tell, we're going to go into the paper from Ha Dome and Daniel Marcoux from 2005 who participate in DUC, which was a long-running challenges or the yearly kind of shared task on the building a summarization system. And then I was reading their paper. It's pretty well written. It's very fun to read because they're saying that everything is breaking down. But then what you notice is that essentially there is no objective way to tell what the quality of a summary is. So in this DUC, they had a bunch of different metrics they use in order to evaluate or to rank different automated summarization systems. And then some of them, or in fact, most of them, require some kind of manual evaluation as well. And even then, the rankings of all these participating systems wildly changed from one metric to another, meaning that this intrinsic evaluation perhaps is impossible to start with. Maybe it's just difficult because there's no single objective measure of the quality, but there are many different aspects that need to be captured. So the biggest issue is that it's very, very ambiguous, right? So there were 5 questions that they asked in 2005 about the quality in order to measure the quality of summarization system or the summaries generated by summarization system. Question number 1, grammaticality. So ungrammatical sentences should not be in the summary. It sounds very naive and then it sounds very innocent. That's not true. In fact, you notice that there is no such thing as D grammar for any of the languages that you actually know. It's a weird thing. So, okay, so slightly ambiguous. And then the second question, no redundancy. There should be no unnecessary repetition. And then you're like, makes sense, okay. But then you start thinking a bit, and then what if I actually repeated a phrase in order to emphasize a point? Is that considered unnecessary or necessary? It turned out that this necessity of the repetition is again not a clear-cut binary metric that we can decide, given any repetition, necessary or not. A bit ambiguous. And then referential clarity. There should be no dangling references. But then again, so dangling references within a summary may be clear-cut, let's say, criterion. However, because the summary does not exist on its own. In fact, summary is provided to a person in certain contexts. So the dangling references on themselves within a summary do not necessarily mean that those references are not really referring to anything, nothing. It might actually refer to something that everyone agrees on, like some kind of common sense, let's say, entities. Right? So still a bit ambiguous. There's a focus. There should be no sentence containing irrelevant information. Who decides which information is relevant or not? Difficult, right? And then it has to be a coherent body of information. I don't know. What does it even mean for information to be coherent? It's so ambiguous, right? So it's very difficult. And then another thing that we notice is that a lot of people then decide that, okay, if we cannot give a nice set of criteria to tell what the quality of the summary, then what we're going to do is we're going to simply ask people. We humans should be the objective judge of the quality of the summary or the text or any kind of, let's say, generated text, right? It turned out that that's not necessarily true. So I actually did some experiments earlier on trying to evaluate the open-ended chatbots. And then we wanted to evaluate it as objectively and as well as possible. So what we did was to spend tons of money on Amazon Mechanical Turk to get the scores, right? So what we did was that we asked the Turker to talk to one of the chatbots. And then after about 5 to 6 turns, we asked them, okay, how did you like this conversation? Please give us a score between 1 and 5 or 1 and 4. We thought, okay, if humans are of the very, the objective judge of the quality of this open-ended generation, then this should be the best way to go. Turned out that that's not necessarily true. So on this slide, you see 2 systems, and then each row corresponds to each Turker, and then each dot corresponds to the conversation they made with the chatbot. And then on each plot are the conversations against a single chat. What you see is that it's essentially random. Some people are too generous. Some people are too harsh. Some Turkers just don't think that much. Most of the Turkers just converge towards the score 3, which really doesn't mean anything. So in other words, everyone, even ourselves, has their own standard and variance, and then relying on, let's say, humans as an objective judge of the quality of the summary or any kind of open-ended text generated by machines turned out to be a bit of a difficult matter. We'll have to just collect thousands or the tens of thousands of scores from humans, but that's quite expensive and difficult. And then at the end of the day, you notice that if you wanted to do the automatic intrinsic evaluation, it's bound to be hard, if not impossibly hard, because getting the perfect automated intrinsic evaluation metric is equivalent to building a perfect text generator as well. Because if I have the perfect automatic intrinsic evaluation or the metric, then I'm going to use that to just score all possible summaries, pick the one that was scored the highest, and then I'm going to just give it to you, right? That's going to be my summarization system. So it's just very, very difficult. So instead, what people have been thinking about over many decades is to use so-called extrinsic evaluation. That is, how this summary be used in the downstream. That is, you generate a summary, and then you send this summary to the intended audience, and then that audience is going to use that summary to do something, and then we're going to say that the quality of the summary correlates well with how well the audience of the summary did whatever they were intending to do. In 1992, Maurice et al. Proposed the question answering or the reading comprehension as one such downstream task. The idea was you start from some paragraph, you use a summarization machine to summarize this paragraph. And then we're going to give either the paragraph or summary together with a question to the test takers. And then test takers are going to answer the question based on either the paragraph or summary. If the test takers agree with each other between using paragraph and summary, then the summary is perfect for solving this particular question. And then if you do that for as many paragraphs as possible and as many questions as possible, and then what you can check is the agreement rate between the test takers who are given either the paragraph or the summary. And then the funny thing is that I highly recommend you to check this paper out from 1992, because I believe this is the first paper where their abstract was automatically generated by their own summarization system from their own main text, main content of the paper. And then it's amazingly well written abstract. Okay, sounds good. But then reading comprehension sounds a bit tricky. I'm going to talk about why it's tricky. So what if we go for something slightly easier? So in 2005, two different groups proposed the very same idea called the relevance prediction. So instead of solving the reading comprehension problems, because solving those questions actually does require to be prepared. So instead, what they are going to do is that what is the thing that everyone does these days? We all use Google. We all use Baidu, or we all use Yandex, or whatever the search engine. So one thing we do is that we use search engine every day. So then what we're going to do is we're going to ask user to provide a query, and then we're going to query the search engine with the query that was provided by the user, and then we get bunch of documents retrieved. And then we're going to ask the user, okay, given these 100 documents, can you tell us for each document whether the document is relevant to the query that you issued? So we now have a relevant documents and the irrelevant documents. And then after about a month, we're going to come back to the user, and then we're going to show them the summaries of those documents. And then given those summaries, we're going to ask them again, okay, can you tell us whether this summarized document is relevant for the query that you issued a month ago? And the idea is that if the summary of the document was good, then this relevant judgment or the relevant prediction should stay as it is. So document should be relevant even when its summary is relevant. And then if the summary and document are deemed either relevant or irrelevant, but always in agreement, then we say that the summarization system is great. So this sounds pretty nice, except that it turned out that the determination of the relevance of a document for many of the queries is very difficult on its own. So to summarize the extrinsic evaluation part, it's definitely better because often there's much less ambiguity. So think about comparison between the goal-oriented dialogue versus chit-chat. How do you tell the quality of chit-chat? Nobody can tell the quality of chit-chat easily. But if it's a goal-oriented dialogue, you can simply tell whether you have achieved the goal that you intended at the beginning or not. And it's better because it's much more easily quantifiable. In the case of the reading comprehension, we simply say, how many questions did the test taker answer correctly given the summary of the paragraph instead of the original paragraph? So we can easily tell the quality of the summary. However, extrinsic evaluation also has some downside because we gotta actually prepare the evaluators. If you want to use the high school science exams in order to check the quality of the evaluation, summarization system, then we need to actually have high school students who have been trained to take these high school science exams. And you'll be surprised how surprisingly difficult high school science exams are if you suddenly are asked to take them now. And second disadvantage is that often these evaluation tasks are not natural. If you have taken TOEFL, TOEIC, or IELTS, I don't know, the British version of the TOEFL, then what you notice is that many of those reading comprehension questions are, pretty unnatural, right? They are artificial. So there is a big question of whether using these downstream tasks actually implies or correlates well with the quality of the summary because of the naturalness or the artificial nature of many of these questions. However, regardless of these two disadvantages, because of the two advantages, the lack of ambiguity and the easy quantifiability, I personally prefer extrinsic evaluation, and then we're going to stick to this for now. Now, unfortunate thing about all these evaluation metrics, either intrinsic or extrinsic, is that we need you to participate and then score all these summaries. And then as the text generators get better and better, we tend to generate longer and longer text. And then unless you are extremely dedicated, you are not going to read the entire thing in order to provide a single scalar score. And then we're going to need hundreds, if not thousands of them. So, like today, I want to narrow down on the factual consistency aspect of the summarization. And then the question is the summary factually consistent with the original document? So here's the original document, here's a summary. The question is that does this summary only contain information or the facts that are consistent with the facts within this original article? And then in fact, it's been 27 years since Maurice L. proposed this idea of using reading comprehension. And last year, a bunch of people, including myself and my students and other groups from all over the world, just had the epiphany suddenly, right? Saying that, oh, wait, hold on, we can use reading comprehension to evaluate the quality of the summary. So how does it work? Let's just go through it quickly before we take a break. So we have an original paragraph on the left-hand side about the steel pipe that is going to pass through the crude across the, let's say, gigantic continent kind of thing. You don't have to read it at all. And then I actually read it and then created three summary sentences, three potential summary sentences. Summary one, the pipe delivers 2 million barrels of crude oil across tundra. Summary two, the 4-foot wide pipe carries 84 gallons of crude each day. Summary three, or the candidate summary three, the 4-foot wide pipe carries 84 million gallons of crude each year. They all, if you only looked at each one of them without looking at the original paragraph, you will say that the summary makes sense. But then now we want to know, given this original paragraph, which one of these three summary candidates is best. So then what we're going to do is we're going to look at a particular question. And this question asks for how the frequency of the, let's say, oil travel, or the 84 million gallons of oils travel through the pipeline. And then if you read the original paragraph, the answer is a day. So each day there are going to be 84 million gallons of oil that travel through the pipeline. Now, let's forget about the original paragraph. We'll try to answer this question using one of these candidate summaries. Now, let's look at the first summary. The pipe delivers 2 million barrels of crude oil across tundra. And then you try to answer this question, you realize that, oh, okay, it's impossible to answer this question. Now, let's look at the second summary. Now, you notice that by looking at the second summary, you can answer this question perfectly by answering that the answer is a day. And then that agrees very well with the answer that you would have gotten had you looked at the original paragraph. Now, looking at the summary, the third summary candidate, unfortunately, the answer changes. The 4-foot wide pipe carries 84 million gallons of crude each week. So the answer is going to be B, which does not agree well with the answer you would have gotten had you looked at the original paragraph. Although if you only look at the summary, the third summary, it looks really almost perfect. However, it's not factually consistent. So this is the focus that we're going to have. So now I've talked about the kind of basic ideas behind the evaluation of the open-ended generation, and in particular the summarization. And if you have any questions, let's try to ask the questions I answer before we move on to how we can actually do it better than 1992.
Okay, great. Thank you for this first segment. I will share the screen so that we can
okay.
see the questions. Just a second.
Should I stop presentation first, or?
No, it's fine.
Okay.
It should go over yours if I can just find mine. Just a second. Where is it's not showing up? It's coming.
Okay.
For some reason, it doesn't. Yeah.
Ah, yes.
Got it now? Sorry about that.
Yes, I can see it.
Do you recommend using RL for summarization, or what other NLP tasks can be solved with RL?
Ah, yeah, this is a really interesting question. And then I do know that a lot of people at the summer school are into RL in general, so I have to answer it really, really carefully. But I think, of course, the reinforcement learning is one of the most generic paradigm that you can use for training any kind of machines, because all you need is, in fact, the reward function that could be either sparse or dense, differentiable, maybe non-differentiable, it doesn't really matter. However, what it means is that it actually does miss a lot on what the available information. So what you want at the end of the day, in order to build an actual system that you want to deploy, is to use all the information available in order to reduce the variance as much as you want, and then make a training system or the resulting model to be as predictable as possible. And then in order to do so, in terms of summarization or any kind of natural language generation test, what we have is that we have a bunch of text that has been already generated by people. We sometimes have the reference summaries. We sometimes have just a bunch of summary-like text, although there may not be a perfect correspondence between the examples that you have. And what you can do is you can actually use all those information on top of the reinforcement learning algorithm. And then what that actually implies is that the learning paradigms that we think about in machine learning, in fact, is not a set of discrete paradigms, but more like it's a spectrum. So on one hand, we have the reinforcement learning or the bandit-like algorithms. And then on the other hand, we have a supervised learner where we have the amazing amount of information or the supervision on what should happen given each instance. And then in the middle, there are many different algorithms going from the unsupervised learning to imitation learning to all those, let's say, model-based, let's say, reinforcement learning and whatnot. So in a sense, this answer is Of course, yes. However, when you build the actual system that solves the actual problem, you actually have to think about the problem itself and then think about what are the information available. And then you need to come up with or design or customize the learning algorithm to maximally utilize such information.
Great, thank you. Doesn't the same problem exist when evaluating machine translation? What are better alternatives to Blue score?
Yep, so the same problem exists for machine translation as well, however, to the lesser degree. So machine translation is not particularly an open-ended generation in a sense that there are often a single best translation, or at best, and most, let's say 2 to 3 best translation. So one thing that a lot of people are kind of, let's say, confused about is that what is this problem of translation? So do we take the translation as just generating a text in a target language that's going to have the same meaning as the source text? Or do we take translation as the translating the source sentence into the target language as faithfully as possible, even at the syntax level? So, and then often when we think about machine translation, we're looking at the latter. And in that case, we have a very particular, let's say, right translation almost always. So that's why we have the same problem, but to the lesser degree. And then, of course, there are many different, let's say, new evaluation metrics that are being proposed for machine translation, but it's not as urgent as evaluation metrics for summarization, which is just a complete mess. Yes.
Okay. What's your take on perplexity metric for language modeling?
Oh yeah, perplexity is an amazing metric, right? So at the end of the day, of course, I'm very much subscribed to this kind of, let's say, probabilistic machine learning. And then perplexity is really nothing but just computing the log probability. You just exponentiate it at one point. So in that sense, perplexity is the best way, in my opinion, to tell the quality of the language model you're training. Now, of course, that does not mean that this language model allows you to generate something good, right? Because what perplexity captures is how well this language model can score the existing, let's say, written text. So how well we can generate from this language model now needs to rely on this kind of extrinsic evaluation, because the text on its own doesn't really mean anything. So in which context it was written or spoken, and then in which context it's going to be read or heard, and then in which context it's going to be used, all matter. So, if you want to use language model for generation, perplexity shouldn't really be used to tell the quality of the language model. But when we say language model is a scoring model. It's an unsupervised machine learning technique. So perplexity is great. I mean, I think we should all use perplexity. But of course, if I were to just add one more thing, there's always an issue of using the average score to tell whether your machine learning system works well or not. That's a really big issue. And especially in language, or I think many of these structured prediction domain, the average score can be very deceiving, because often the phenomena that we run into are from tail. So these average scores are going to tell us how well the machine works in the head, but it's not going to tell us how well machine works in the tail. So that one is actually what matters often. And then to do so, we can rely on perplexity, just that you will have to look at the perplexity for different categories of the data.
Okay, great. Maybe we take a few more. Is it possible to process natural language directly from speech or audio signals, and how to apply NLP techniques to such continuous signal?
Yeah, this is definitely possible. There are a lot of people who are working on trying to tackle the speech-based natural language understanding. So NLU is an overloaded term, but the natural language understanding in particular is used in practice to build a goal-oriented dialogue system. And then to do so, there are a lot of, let's say, problems like, oh, I have a template. Now I need to fill in the slot based on the text or based on the audio. Often what has been done, and then what is still being done, is that you have a very nice automatic speech recognition system, and then you have a slot filling system, and then you have a dialogue state tracking system, and then you now have a template-based generation system. And then what happens is that the error accumulates. And then that's why you see all those, let's say, weird mistakes that Siri or Google Assistant made. And then that's because the errors accumulate every stage. And then if you look at individual stage separately, these stages are amazingly well implemented. Their error rate is very low. But as you know, the error accumulates very rapidly. And then at the end of the day, the answer you get is completely irrelevant to what you ask. So one of the things that a lot of people have been working on, especially starting with some of the work from the Gregor Mesniel, who is now in Google, if I remember correctly, in 2013 and 14, is that let's try to build a speech to, let's say, slot filling system. And then Dima Sardou at Montreal has been working on this direction more recently. And then the nice thing there is that we are essentially skipping the stage of turning this continuous signal into the text, and then turning the text into the slots, or the candidates that can go into the slots, because we can go directly. But the issue is that it's not easy to come up with the data, because we can have a lot of data that turns the text into these slots. We can have data that's going to turn the speech into text, but we rarely have the data that goes directly from speech into these slots or whatever the other things that you want to predict. So we need a lot of, let's say, advanced machine learning techniques like the self-supervised learning and the unsupervised learning. And in particular, you need a way to do the automated or the unsupervised pairing between the two different modalities. So the techniques from the unsupervised machine translation matters. Techniques from those optimal transport are going to be very, very useful in the future. So it's unsolved problem, but definitely there is a huge, let's say, opportunities there.
One more question about video summarization. If you have in mind any paper to recommend about that.
Yeah, I mean, there are a bunch of papers. I mean, I had a paper a long time ago, but I don't think anybody should read that anymore. There are many papers, I think, from the Columbia, like the Shifu Chang. So he's a pretty famous person in information extraction. And then what he's been spending the past, let's say, decade or so is to build an information extraction system that is able to look at not only text, but the associated images, associated video clips, and everything. And then his collaborator, Hung-ji, who is now a professor at UIUC, so she's been the one who's been building all these systems. And then these multimodal information extraction systems are amazing in the sense that you can add whatever the modalities you want, and then it's going to give you not a very fluent natural language description of the video or the events that is being taken, but it's going to actually give you a very precise, concise representation of what is happening within the video together with the text. So I think if the goal is to solve that problem, that's the kind of, let's say, group of people that you need to follow. But if your goal is to come up with a machine learning algorithm that is able to work with the different modalities, then you need to look at the multimodal machine learning people. So it's a kind of two different things, as I talked about at the very beginning. Right. There are people who actually build these, like the real world systems. And then there are people who are trying to come up with the algorithms that can potentially in the future be useful. But it's very low chance in general. That's the difficult part about working with the algorithms. So then, unfortunately, you need to follow these two different groups of people in order to know about what is going on in both sides.
Right. Okay, just one last one. Is there a way to combine both intrinsic and extrinsic evaluations?
Yeah. So in a sense, yes. So often what ends up happening is that there is never going to be a single scalar that tells you how well the system you have built works. In a sense that as your system or the problem that you solve become more and more complicated, these systems are going to have many different aspects that it needs to work well. And then it's going to be very unlikely that it's going to work well for every aspect you want it to work well. What it means is that you need to be able to tell for each aspect how well this system works. And then one of those aspects will only be evaluated by the intrinsic evaluation. For instance, the fluency. I mean, fluency is not a thing that we can measure because it's not really anything objective. So we'll have to rely on, let's say, humans or the users to tell us how fluent this text is. So yes, the answer is yes, but I don't think it's going to be mixing them into a single scalar because that's just not going to be possible.
Okay, let's thank you for answering these. Let's move to the second segment, and then we'll take a few more questions at the end.
Okay, sounds good. Those were great questions, by the way. Yes.
There are still many coming, so
all right. So yes, so we talked about the reading comprehension as a way to
could you just please do share?
Oh yeah, okay.
Because it's not full screen now.
Yes, okay.
Yeah, perfect. Thank you.
So in the first part, we talked quite extensively about the importance of evaluation and how the extrinsic evaluation is my favorite and then has a desirable properties. And in particular, we looked at the example from the Maurice et al. 1992, where they proposed to use reading comprehension as a way to evaluate a summarization system. And then, of course, we want to use some reading comprehension, and then we want to test it whether it actually does make sense to use it to evaluate the summarization system. Unfortunately, only if I could ask ETS to create TOEFL questions for any summary that I generate or that my machine generates, and only if I could ask all of you to take TOEFL every day for my own research. I don't think either is going to happen. So then the idea is that what if we actually replace ETS as well as all of you with the neural networks? As we saw at the very beginning, these neural nets have started to be an amazing text generator and also an amazing question answering system, as Tomasz may have told you. Now, of course, Tomasz probably told you that everything has to be logistic regression, which up to a certain level, I agree with him. But of course, you'll never be able to build a logistic regression to, I don't know, solve the amazing reading comprehension problems that well. Tomasz might be able to build one, but I don't think anybody else can do it. So we're going to stick to the neural network that are very, very deep. So only if I could replace ETS and all the human annotators with the neural networks, then I might be able to use this reading comprehension to evaluate any given summary against not a reference summary, but against the original paragraph in terms of the factual consistency by letting neural net generate questions on their own and then answer them again on their own. So we're going to remove the humans from this loop so that we can use it for automatically evaluating the summarization systems. And then that's how we end up with so-called KEX, that is the question answering and generation for evaluating summarization. So this might be the only equation that I'm going to use in the entire lecture. So let's look at this. So what we are going to compute is the expected agreement between answers based on the original passage, so that's the original one, and its summary using questions generated from the summary. So what we're doing is that we are given now an original passage and its summary. And what we're going to do is take the summary, use a neural net to generate a bunch of questions. And then we're going to use yet another neural net to answer these bunch of questions based on either the summary or the original passage. And then we're going to look at the agreement between the answers generated from these two scenarios. If they agree really well, we're going to say this summary is great. If they don't agree well, then we're going to say this summary is not of a high quality. So let's look at the question generation. What we need is an answer conditional question generation, in a sense that we want to generate as good a question as possible. And then in order to do so, it turned out that it's a good idea to build a neural net that's going to take as the input the original passage or the passage, and then the candidate answer. And then this neural net is going to create the questions for you. And then it's not a new thing. People have known that we can actually do that since like 2016, 17. But starting from last year, with all these amazing pre-trained language model, it turned out that we can generate amazingly fluent questions. And of course, we do a bit of a basic filtering and so on, but it turned out that one wasn't that important. And we use transformers here. So you're going to learn about transformers later. But it turned out that using transformers does make the questions amazingly fluent. Now, questions have been generated. Now we need to answer them. And for answering questions, we again use the neural network. And we start from BERT, and then we fine-tune the SQuAD 2.0 data set. And then it's an extractive question answering model, although it didn't have to be extractive question answering. And then what this neural net or the question answering model does is to try to answer this generated question, either based on the original paragraph X or its summary Y. So this model is going to give us two different answers. And then now we have the we need to check the agreement. Now we have two answers, a pair of answers. Now, how do we know that they agree with each other or not? In the simple classification, it's very trivial, right? So if given an image, if the classifier says cat once, and then if another classifier says cat, then that's it. They agree or not. But in the case of natural language, especially in this kind of structured prediction, in fact, checking the agreement itself is very complicated. So in this particular paper where we propose this evaluation metric, we just use the token level F1 score. It's pretty horrible, I agree. But because the answers are generally short, it turned out that it works relatively well. However, eventually what we want is that if we want to use some kind of divergence in the distribution level. So we want to get the distributions over all possible answers from these two, let's say, question answering models, or a single question answering model that solved the question twice using either the original passage or the summary. And then we want to compute the divergence directly, but we haven't done that. But that's a kind of future direction that needs to be studied. So, and then we end up with this KEX. So let's look at the whole process once more. So we have a source, and then we have a summary. So we start from source, and then some kind of black box summarization system is going to give us the summary. And then given the summary, a neural net is going to generate a bunch of questions. And then for each question, we're going to ask yet another neural net to answer based on either the source or the summary. And then we get a bunch of pairs of answers. And then we're trying to look at whether each pair of answer agrees with each other. And then we're going to look at the rate of disagreement. And then that rate of agreement is going to be directly proportional to the quality of the summary. Now, of course, how do we know that this works? In order to know that this works, we had to effectively ask Turkers to work like humans, work like neural nets, and then tell us about the consistency or the factual consistency. And then, as I said earlier, it's very, very difficult to evaluate summary because you will have to read the entire article, you will have to read the entire summary, and then tell us whether this summary is good or not. It's not easy. So instead, what we did was to make the problem much more narrowed down for the factual consistency, as I talked about earlier. And then we're going to show only one sentence at a time of the summary. So we show one sentence from summary, and then show the original article, and ask the Turker, does this sentence, a single sentence, agree with the original article? And it turned out that that's much easier to answer than asking them to assess the quality of the entire summary. So we're simply saying that, okay, here's a sentence. Does this sentence contradict whatever has been said in the original article? It turned out that this one is much better. And then the agreement rate among the Turkers was reasonably high, so that we could actually use this annotation or the gold consistency scores to tell whether all the other automated evaluation metrics made sense or not. So we collected a bunch of them. Now what we do is that we're going to look at a bunch of those automatic metrics, and then trying to see the correlation between the automatic metric and the human consistency score. Let's start with the ROUGE score, because the ROUGE scores are the ones that are being used for authors to boast how awesome their summarization systems are. It turned out that the correlation against the human judgment is pretty low. Let's say 20, let's say Pearson correlation coefficients about 20 on CNN Daily Mail dataset, which is reasonably simple dataset. What it means is that essentially we cannot use ROUGE score in order to tell whether the summarization systems are good or not. Now, Meteor is another metric that was developed for evaluating machine translation system. But of course, people do use it for summarization as well as all the other natural language generation tasks. Doesn't help. It's just as good as the ROUGE scores. How about BLUE scores, which were designed and then are de facto standard for evaluating the machine translation systems? Same thing. So it turned out that ROUGE, BLUE, Meteor doesn't really matter. Now, BERT score is the score that was proposed more recently by Yoav Arsi and his students from Cornell Tech. And then there, the idea is that they use pre-trained BERT, which is amazingly well trained. And then they look at the Earth mover distance or the optimal transport cost. So it's going to be a Wasserstein 1 distance between the set of vectors you get from the BERT. And then you look at the set of vectors from the reference summary, set of vectors from the generated summary. And then you look at how similar they are. It's okay. It's slightly better than any of the other scores, but you can't really tell the difference. And then the one thing I want to point out is that all these metrics do use or do require you to have the reference summary. That is a human written summary in order to check this the quality of the generated summary. Now, we apply this text on the same set of summaries generated from the text. And then in this case, we don't really need the reference summary. All we need is the actual original passages. And then it has a much higher correlation against the human judgment. And then what it actually does make sense, because in this particular case, human judgment corresponds to the factual consistency. And then the text or the reading comprehension, almost by definition, asks about the factual knowledge embedded in the original passage. So text should have had a higher correlation, and then this just confirms this. On the other hand, as I said at the very, very beginning, all these n-gram matching baselines cannot capture the factual consistency because they don't really discriminate between the factually salient portion of text versus factually non-salient portion of the text. So we tried it on another data set that is called XSUM. This, by the way, is a horrible data set. No one should work with it, but it's one of the most widely used large-scale summarization data sets, so we use it. And then we see a very similar trend. ROUGE scores are not going to work well. Medio, same level. Blue, same level. And in this particular case, somehow the BERT score completely failed. We actually have no idea. We need to look into it. But my belief is that it's just a peculiarities of the XSUM, this data set alone, that make comparisons of all these metrics a bit incoherent. And then the text does work better, but still the whole correlation is much lower than before, compared to the CNN and Daily Mail. But again, this is probably because of the artifact from this data set construction process. But we do see that regardless, the proposed approach, that is this automated extrinsic evaluation, actually does give us a better correlation against the human judgment, because it actually has an idea of what are the salient portions of the text that the evaluation metric should focus on. And then we looked at some of the other, we looked at the impact of the different hyperparameters of this evaluation metric. So the unfortunate thing about this kind of learning-based evaluation metric is that the metric alone now has number of hyperparameters of the knobs that needs to be tuned. And then in particular, there are three major knobs that need to be tuned. One is that the quality of the question answering system. And second is the quality of the generated question. And then the third is the number of questions that we're going to generate. It turned out that this metric is very robust to the quality of the question answering or the question generating systems, which is very good. But it was really important to generate as many questions as possible. And then it kind of, is understandable because, as I said earlier, it's all about the tail phenomenon. So we want to generate as many questions as possible in order to cover as many aspects of the factual, let's say, knowledge as possible in the original passage or the summary, in order to tell that whether this summary is consistent against this original passage. So let's look at one particular example. This is one random article that we took out of the CNN Daily Mail data set. And then on the left-hand side, you have the original article. On the right-hand side is an automatically generated summary. And then now on the bottom, I'm going to show you the automatically generated question as well as the answer based on the article and the summary. And then none of these was manually generated. These are all automatically generated by the neural networks. So the first question, what did the attacker have? Based on the article, neural net said a large knife. Based on the summary, neural net said that the knife and a fire extinguisher. And then so we know that it's partially correct or the partial agreement. And then we can do the same thing over and over. And then sometimes we're going to see that the answers agree very, very well, but other times only up to a certain level. And of course, sometimes it's incorrect. There is a huge disagreement because the factual consistency of the summary for the particular aspect that corresponds to a generated question is not high. And then simply averaging this agreement rate gives us the quality of this summary. And then the nice thing is that it's very interpretable, right? You look at the generated questions, you look at the answers, and then you look at whether the answers disagree with each other or agree with each other. And then by looking at the disagreed answers and the corresponding questions, now you can tell what was a particular aspect of this summary that was incorrect in terms with respect to the original article. And then that's how you actually get the interpretability out of it. Because this whole process is based on natural language, we now can tell what is going on inside. So to quickly wrap up, this CACS allows us to do the evaluation without any reference summary. That's great. And then it is interpretable and it's extrinsic. So it has a much lower variance in general. And then it actually does tell us a very precisely quantified level of the quality of the summarization system. And then the nice thing is that it turned out that the whole field, including natural language processing, machine learning, have been collecting all this nice data and then building all these nice machine learning algorithms so that we didn't have to do any CACS, this evaluation metric specific data collection, nor the customization of the algorithms themselves. So we could actually use the off-the-shelf data, off-the-shelf machine learning algorithms, and then just put them together in a way that made sense. And then it ended up being a very nice evaluation metrics. So one thing that you notice now is that the evaluation now is a part of machine learning or the learning, in a sense that we are now building a virtuous cycle between learning and evaluation. Before, we used to think that okay, evaluation has to be something that is separate in order for us to use it in an objective manner to tell the quality of the outcome of the learning algorithm. But that's not necessarily true because that's too limiting. What we need is that as the learning algorithms get more and more sophisticated, evaluation metrics need to catch up with it in order to tell the quality of those sophisticated learning algorithms. And in order to do so, the evaluation metrics themselves will have to benefit or exploit the advances in learning algorithms. And then, as with any other advances in the field, my group is not the only group that has worked on this. There are a bunch of the other groups have simultaneously thought of this direction and started to push out the papers and the ideas out there. And then I'm listing, let's say, a bunch of papers in this slide. If you're interested in further, you gotta read all these papers. And these are really very interesting and well-written papers that I like. So just two future directions that I wanted to push forward. One unfortunate thing about CACS at the moment is that it's very, very sensitive or is very dependent upon the choices of the question answering and question generation models. So what we want, in my opinion, is that we need to marginalize those question answering and generation models as well. And then that is going to correspond to having two more expectation in this CACS formula, meaning that we want to try as many question answering as well as the question generation models, just like we were trying many, many generated questions. And then that's going to make it much more robust to the choice of the QA as well as the QG models. And then I just named it already, and then it's going to be called Bayesian CACS. And then the second thing is that we want to be even more Bayesian in a sense that we want to be meta Bayesian CACS. The idea is that we focus on this reading comprehension, but don't we actually want to come up with a metric that takes into account as many different tasks as possible that are relevant to your actual problem. And then in order to do that, we'll have to marginalize out the task as well. And then we end up with the Bayesian or the meta Bayesian CACS. This one, I have absolutely no idea what is the right way to go, but I think that this direction is going to allow us to really build a robust and solid evaluation metric for the summarization system, as well as any kind of open-ended natural language generation systems in the future. And then that actually concludes my lecture, and then if you, I'll be happy to actually stay around and answer any questions.
Great, thank you so much. So it's good that you're available for more questions because we do have those.
Okay, perfect.
I am sharing those now.
Yeah.
Okay. What would you suggest for summarizing very field-specific text with limited data?
Yeah, so this is an interesting question because yes, summarization system, there is no such thing as a universal summarization system because summaries are very audience specific. So, but however, that doesn't mean that we cannot use any of those existing work on the summarization system. So my suggestion would be to start with the well-trained, pre-trained language model. And then there should be two things that need to be done. One is that, of course, trying to fine tune it on your target data, that is, however limited that is. And then what we see is that these pre-trained models are extremely good at being fine-tuned or adapted quickly. So that's going to be useful. However, there's going to be only one aspect. The other aspect that needs to be considered is that the fact that you are working for a very specific field implies that you are going to be able to collect not only the data, but also the bunch of, let's say, constraints or the rules that need to be followed for the particular domain. Then those rules can be imposed not in the training time, because in the training time, it's unclear what is the right way to impose the rules so that in the test time, those rules are going to be satisfied. But in this kind of generation scenario, because we need to solve a very difficult inference problem or the argmax problem, we use a lot of complicated but often heuristics-driven algorithms there, and then you can actually impose those rules in this generation process. And I think that's going to be very important if you're going to deploy this for a mission-critical applications in a particular domain. So think about it from two directions. Now we need to train a system to generate text that looks like a domain-specific summary, and then you need a generation algorithm that tries to generate or to rule out any text that's going to dissatisfy or to violate any of the rules that you have collected.
Thank you. Can Ngram's approach be used for evaluation after applying part-of-speech tagging on original text to remove articles?
Right. So yeah. So this is an interesting thing. This is how you rediscover the reals that was discovered about 3 decades ago. Is that so when people started to compare different texts before neural net or anything like that, they looked at the word overlaps. But then we all immediately realized that word overlap is a difficult thing to use because it's often going to be dominated by the words that have nothing to do with the actual meaning of the text, like all those functional words, the, all, is, am, all those things. So then people started to make a list of those so-called stop words and then remove them when they do the word matching. And then that actually helped. But it turned out that coming up with a list of the stop words is a bit difficult because first of all, the list grows, and then there is no kind of, let's say, standard list that everyone goes to. And then the list is very domain specific as well as language specific. So then people wanted to come up with, okay, what if we can come up with the kind of list in a statistical way? And then that's how you end up with those TF-IDF. That is the term frequency and inverse document frequency. That is, you're going to look at each of the words, and then within a document, look at how often the words appeared, and then within the entire, let's say, collection that you have, how often that term appeared. And then any word that appeared enough in the entire collection of the documents, but do not appear enough in each individual document is a very salient word. And then people started to use that kind of more smooth weighting in order to tell what are the ones that needs to be removed and then what are the ones that needs to be considered further. So the answer is yes, in a sense. However, this is precisely the issue with the rule-based system. Coming up with, let's say, the kind of, let's say, criteria manually, and then trying to scale it up is very difficult because you always run into all those exceptions, and then you realize that all those rules or the list of the things that you want to take into account turned out to work only for a very narrow domain and so on. So in a sense, we need to be able to mix them in a right portion to make it work better. And in the particular case of the text evaluation, removing those stop words makes sense. However, those stop words often do imply, like they impose a very important constraint on the meaning itself. So you don't want to actually remove them. So you want to use this BERT score or any kind of continuous representation-based evaluation.
Okay. Is it a good idea to use multiple text classifiers, like tens of them, for comparing two summaries applied on each of them, probably from point of view of content, language quality, and compare the results?
Yes, precisely. So that's going to be like the Bayesian case that I talked about is that so whenever you want to, so there are two scenarios where the machine learning systems are used. One is that you deploy it and then you just look at the decision made by this neural network. In that case, you just want to build as good one single amazing machine learning classifier or one, right? But the second scenario is that you want to actually use these neural networks in order to get the insight into the data. And then in fact, that's actually the majority of what data science and machine learning actually, or statistics is that, we want to get the insight about the problem itself as well as the data itself. And then in order to do so, we have to use as many classifiers as possible because these neural nets are not identifiable, meaning that if every neural net that we train is going to be on its own unique, and then it's going to have its own idiosyncrasies. And then what we want is that we don't want to be drowned by the particular idiosyncrasy of each individual classifier, but we want to look at as many classifiers as possible and then remove all those, let's say, peculiarities of the individual classifier. And then look at only either the intersection or the union of the important features coming out of this neural net in order to get the insight of the data. So the answer, well, that was a long answer to a very concise and precise question. And then the answer is yes, we want to look at not two, but as many classifiers as possible.
Great, thank you. How do you evaluate the questions generated by the neural network? How do we know the questions are good enough in the first place, even before the summary or answers?
Yeah, this is a great question. So the one thing is that just eyeballing them turned out to be great because these neural nets just generate so fluent the questions already. It's impossible to tell whether it was neural net generated or human generated. However, of course, there's a question of, but the better question is that do we need to have a high quality question generation system? And then it turned out that so empirically, it turned out that the quality of the question generation system doesn't matter that much as long as they are of a reasonable quality. So that's the one thing I showed you in the ablation. I didn't have time to go through the individual plots carefully. And then the second thing is that the weirdest thing about this CAX or this kind of extrinsic evaluation is that it's about the agreement between the outcome from these two neural networks. Even if they are horrible neural networks, if they actually end up in the same decision, regardless of they start from the summary or the article, then there is a good signal that the summary has the same information as the article. So what it means is that in fact, solving this QA problem or the question generation problem itself is not really crucial because it's all about whether there is the same amount of information. In fact, what it means is that if there is such thing as the like the reversible neural network on this kind of large, let's say, text space, then this network can very well be random as long as it is reversible because it's going to just carry over all the information. And then if they agree, then that's fine because that just means that they have a same kind of information. So we don't have a good metric to tell how well the generated questions are, but it's likely that it doesn't matter that much.
Okay, great. Maybe we can take two more. What if the answer to the original paragraph and summary are in agreement but actually wrong, leading to confirmation bias? Is there a way to quantify this?
Yes, so this is a really interesting question. Oh man, I have another talk that is kind of along this line. Is that yes, these neural nets tend to make really weird mistakes. And then in fact, let me actually show you this. I might have no, but anyway. So what happens is that these neural nets make a weird mistake. But what we see is that every single neural net we see makes its own unique weird mistakes. There are some overlap, but they make a mistake in a very interesting, different ways. So what it means is that we want, and then that not only applies to the neural nets themselves, but given an individual neural net, these neural nets are amazing in many questions that we throw, But sometimes for very particular set of questions, these neural nets are going to just do something crazy. So, and then those adversarial examples are kind of, let's say, a representative example of that kind of behavior. So what it means is that we cannot really rely on these neural nets for individual examples too much, because who knows, that individual example might turn out to be the adversarial example for this particular neural net, and this neural net is going to do something crazy. And then in mission critical scenarios, you don't want to use them, right? However, that's why in this KEX and many of these kind of extracting the insight from the data or the problem using neural nets, in those scenarios, we use as many examples as possible, and then as many generated decisions as possible, and then as many neural nets as possible. In this KEX, what we do is that that's precisely why we had to generate many questions in order to get the good quality or the good correlation against a human judgment. So that was actually one of the 3+ in the ablation experiment slide that I had to go like quickly skip, is that the more questions we generate, better correlation we get against the humans. Because those weird questions that neural nets fail to answer correctly are drowned out by the questions that can be answered correctly by neural net using either the summary or the passages. So yes. So in a sense that it does happen, that's an issue, but that issue is increasingly rare as we use more questions and more neural networks.
Great. So for humans as well, we are judged by our teachers in school for our summaries, which may be biased, yet we are able to learn. So can this happen for the machines to learn with biased?
Right. Now, this is a trick question. Gotta answer carefully, right? So, in a sense that so of course, we have to precisely define which kind of bias we're talking about here, because what does it mean for the evaluation to be biased, right? And then of course, if you think about the statistical bias and then think about the neural networks, although these neural nets are non-parametric, but we have a very severe limitation on the computation and the amount of data. So these are all biased estimator, statistically saying, meaning that it will actually not work as intended, even if the data that we have collected for the evaluation is perfect. However, often that's not an issue. The issue is that the data that we have collected often have an issue with some unintended, let's say, the systematic bias being encoded, and then that might actually throw the whole thing off. And then that actually is true in this particular case of the evaluation based on learning algorithm, is that if the learning algorithm itself is easily thrown off by the systematic biases encoded in the data, then that's going to also throw this evaluation metric. So of course, what is the right way to go? I don't think anybody has an answer, like the answer to that. But one way I see as a kind of, let's say, way to avoid this kind of, let's say, weird, let's say, particular bias affecting the entire pipeline of machine learning is to agree that, to just realize that these neural nets or the machine learning systems that we build are extremely fragile, in a sense that the individual classifiers are going to have like so many weird idiosyncrasies, and then they're going to capture a very weird particular aspect of the data, which are often the systematic bias that are encoded there. And then we need to rely on having, first, not rely on any individual classifiers. We have to actually rely on a group of classifiers. So we need to be more of the, let's say, Bayesian in this particular case to avoid, let's say, relying on a fragility of individual classifiers. And also, we need to be able to plug in the humans in this loop. So it has to be the loop of the machines and humans in the place. And then the humans can be used as a kind of, let's say, detector of the idiosyncrasies of the machine learning systems that we're building. And then that can go back into this building machine learning system in order for us to improve the machine learning system while reducing the burden for the humans to come in over and over. So recently, there's been a bunch of papers, but in particular, 2 papers, one from the Zach Lipton's group at CMU on making the difference that makes the difference. And also there was a paper from Facebook AI Research from Dow Kill and others about the adversarial NLI, where they actually show that it is possible to build this kind of human and machine in the loop type of system that allows you to both to build a system that's going to be less fragile, but also have the humans so that this whole feedback, there's a feedback loop that allows this loop to detect all those idiosyncrasies and also even the systematic bias embedded in the data, and then avoid that kind of systematic bias by relying on the human's, let's say, judgment and insight. So yeah, yep. So the whole system is going to be thrown up, and then we do see that almost every day in real life, unfortunately. And then what that implies is that we have to be very conscious about the whole thing, and also from the machine learning research side, we have to actually come up with algorithms that are much more robust than the algorithms that we use nowadays.
Mm-hmm. Maybe just one more is still related to biases, and then we are done. Can you please comment on what would be a good metric for quantifying concepts like social bias in dialogue, chit chat, or even summarizing models?
Right. This is yeah. I mean, at the moment, of course, there is no kind of, let's say, leeway, because the social bias is by definition difficult to measure, because it by definition actually evolves dynamically over time. So what is the kind of, let's say, the social bias we need to detect is not a question we can even ask. It's all, let's say, at the moment, are there aspects of the data that reflect the undesirable properties of the society? So that's the question that we need to answer. And then this one, the answer is going to change over time. Now, at the moment, most of the machine learning algorithms that we built are very much driven by data, meaning that it doesn't really have a kind of active components. So it's going to look at the data or the environments and then trying to observe as much as it can, and then trying to mimic what the society or what the data actually exhibits. So, and then of course, in that case, there's no way these models can actually distinguish between the patterns or the regularities arising from the social biases from the regularities that arise from the actual, the non-social, but just how the word is. So what it means is that at the moment, the answer should be that, it has to be the humans, we as a conscious kind of, let's say, being, to be able to intervene on how the machine learning systems work, probably not only at the end stage that is in the deployment scenario, but already from the learning algorithms and so on. So what is going on? We need to be able to understand what the learning algorithms are doing. We need to understand what the resulting models do. And then we need to understand the kind of, let's say, feedback that is created by deploying these kind of systems, and then be able to intervene at every possible kind of points. One point that is missing at the moment is our way to intervene in the learning process. We know how to intervene in the deployment process. We can actually cut it down, or we can put all those rules so that some of the decisions are not going to go into the society and so on. We know how to intervene when we do the validation of the models. It's not easy, but we can actually come up with all those cases, and then we try to check whether these models work well. But what is the right way to intervene in the process of learning itself? That's very unclear. And then that's where probably the idea from the expert systems and so on from the 80s could be incorporated in this learning process, so that we can easily encode in the various, let's say, constraints that we want to impose in the learning process itself. I think that's going to be the most effective way, but our kind of, let's say, existing algorithms don't really allow us to do so that easily. So that's going to be one interesting and particularly fruitful research direction in the future.
Great. Thank you. Thank you so much. Thank you for answering so many of the questions. There are still quite a few questions left. We will create a document, and hopefully you will have time to answer them offline. So thank you so much again for joining us. And